Welcome. In this video, we'll take a look at section 8.1, working with complex numbers. We'll start out with a few definitions to get started, and then we'll jump into some examples. First, we'll start out with the definition of the imaginary unit I. So the number I is defined as I is equal to square root of -1. Which means that I squared is equal to -1. Another property of complex numbers is if we have a negative number inside a square root, so if a constant is positive, then the square root of -a is equal to I times the square root of a. So we'll look at that property as we simplify imaginary roots. Another thing that will be important for us to simplify is powers of I. So the powers of I we have listed here. I is the square root of -1. I squared we can represent as -1. I cubed would be really just I squared times another I, or the square root of -1. So that would be negative square root of -1, which we would call just -I. It's another way we could represent that. And then finally, I to the fourth brings us all the way back to +1. And so this is going to be a nice tool for us to know that I to the fourth is equal to 1 when we go to simplify powers of I in our next example. The last thing we'll take a look at to just prepare us for the lesson is the definition for a complex number. So a complex number is any number in the form a plus bi, where I is some imaginary unit and a and b are real numbers. This is also known as the standard form of the complex number. In our next lesson 8.2, we'll take a look at the trigonometric form of a complex number. So we want to distinguish this form, a plus bi, as the standard form. So let's take a look at some operations with complex numbers. We'll start by just simplifying some roots, and then we will work with some powers of I. So let's take a look at question A, the expression the square root of -32. So when I want to consider simplifying a root like this, there's really 3 components I want to break this down into. This square root we can rewrite with a square root of -1. That's 1 multiple of 32. And 32 itself we can break down as a perfect square times some multiple. And that happens to be 16 times 2. So if we have that string of numbers, -1 times 16 times 2, that would get us back to the -32. And with algebraic properties here, we can split this square root into 3 different roots. So that would be the square root of -1, square root of 16, and the square root of 2. All as a product. Now we can take a look at each individual item. This square root of 16 is simply 4. The square root of -1 we would just represent as an I. And then the square root of 2 doesn't do anything. We have to leave that as a square root of 2. And so that square root of -32 can be simplified down to 4i square root of 2. So this is an imaginary number. And overall, we could still consider it as a complex number that has no real part. So that would be our solution. Let's take a look at another value here and break it down. 63 inside that square root, we can pull apart in 3 different places. First, the -1. Next, if I think about 63, if I wanted to pull out a perfect square out of 63, I think the largest one we could do there is 9. So this would be positive 9 times 7 would give us the product of 63. And so we'll separate these out as -1, square root of 9, square root of 7. And then we'll finally take and transform the square root of 9. We know that to be 3. The square root of -1 is I by definition. And then the square root of 7 cannot be broken down, and we'll leave it on the end. So we have 3i square root of 7. All right, so that's really using our property of the square root of -a, and we're breaking down the roots in those 2 problems. The next couple examples we'll take a look at involve powers of I. So I'd like to simplify these as much as possible with the powers of I. The biggest tool we're going to be using here is the fact that I to the 4th is equal to 1. And so we're going to be utilizing that fact as we break down these powers of I. So when I consider I to the 35th, I want to take a look at this exponent and think about what is the smallest, or I guess the largest, what is the largest power or multiple of 4 less than 35 in this case, or less than my current exponent. What's the largest multiple of 4 less than 35? This is sometimes called kind of a modulus. When we're done, we're going to be thinking about pulling apart the largest power of 4 and some remainder out of 35. So if I think about the largest multiple of 4 less than 35, I think that might be 32. 32 is a multiple of 35 or 4. So we could write that as I times 30, I to the 32nd power. And then I, the leftover powers here would be 3. So we could rewrite I to the 35th as I to the 32nd times I to the 3rd. With our exponent properties, if we put those back together and added our exponents, we'd get back to our starting point. Now let's consider breaking this down further. I know that I to the 32nd, we could rewrite with some exponent powers as I to the 4th to the 8th power. I to the 32nd is I to the 4th raised to the 8th power, because 8 times 4 is 32. And then we also have the I to the 3rd. We know that I to the 4th is just equal to 1, so we have 1 to the 8th power, and then I to the 3rd. Well, I to the 3rd, by definition, we said was -I. That's just -I sitting there. And so 1 to the 8th power times -I is just going to be -I. And so that will be my simplest form that I can put that I to the 35th in. So I, -I. So when we simplify powers of I, my solutions again should be of this form, either I, -1, -I, or 1. Those would be my simplifying forms. So let's consider one more power of I. I to the 17th power. If I consider, again, the largest multiple of 4 less than here 17, I can say that this is equal to I to the 16th power. That's a multiple of 4 times an extra I. That would be making I to the 17th. And again, to break this down, we have I to the 4th raised to the 4th times I. Or we could say that I to the 4th, again, is 1. So 1 to the 4th power times I. And 1 to the 4th power still is 1. So this gives us just I in return. So our solution here for I to the 17th, it's equivalent to just I itself. So that's powers of I and some operations with our imaginary unit. Let's take a look at maybe this little chart next. We have a chart of kind of describing complex numbers here. And complex numbers are kind of a big umbrella for a lot of different types of numbers that we're hopefully familiar with. The first kind of part of a complex number is A, which is the real part. And so if we consider kind of the first category of complex numbers, we would call those real numbers, where the A is not equal to 0 and B, the complex coefficient, is 0. So numbers like 6, -8, -7 over 4, any real number is underneath this umbrella of a complex number. The next category that falls under complex numbers is called compound numbers. That's where we have both an A and a B coefficient that are not equal to 0. So numbers of the form 7 plus 6i, -3 minus I, or 4 minus 2i, all of those we put in the complex number category and the compound number category specifically. So there is a real part and an imaginary part to the number. And the last category is just imaginary numbers. Imaginary numbers, again, is a subset or subcategory of complex numbers that just has imaginary units. So this says the A coefficient here is 0, and therefore there's no real portion of the complex number. It's just the imaginary portion. So we have 7i, -4i, and just the imaginary unit I. We would all call those imaginary numbers. So really 3 branches of complex numbers: real numbers, compound numbers, and imaginary numbers. All right, so the next thing we'll do is working with some operations with complex numbers. And a lot of these are working with compound numbers, more specifically. So compound numbers that have a real and an imaginary portion. So let's take a look at the addition and subtraction. We'll also look at multiplication and division. So first, we're going to take a look at addition. If I have 2 complex numbers and I would like to add them, I'm going to add their real pieces, and then I will add their imaginary pieces. So the real pieces, 3 plus 7, become a 10. And then I can add their imaginary numbers, 4i and -6i become -2i. So we're simply adding the components together, just like we would add like terms in an equation. We'll take a look at subtraction. We want to be careful with subtraction because we are going to be negating everything in that second complex number. So here, let's do this again with subtraction. We have 7 minus 5, that would be 2. And then the next one would be 3i minus 8i, which would be minus 5i. So I have 2 minus 5i as the compound number that's left. The next couple examples, we'll take a look at some products and how we work with these. These are going to be very similar to what we would have as a binomial product in algebra. So we want to treat each of these items as kind of separate pieces to multiply. So I'm going to take the 3, multiply with the real number 2, and with the imaginary unit 5i. This would give me 6, and then plus 15i. Next, we'll take a look at multiplying negative 4i with 2, and again with 5i. So this would give us negative 8i, and then negative 4 and 5 give me 20, and then I'll have I squared on the end. Now it's time to simplify this as much as we can. We have 2 imaginary units. These would be like terms in the middle with 15i and negative 8i. So we have 6, and then plus, this will be 7i. If I consider the negative 20i squared, remember that I squared is simply negative 1. And so this is actually going to be negative 20 times negative 1, which is 20. So plus 20. And we can add those like terms next with 6 and 20 becoming 26. And then we'll have plus 7i. So when we multiply complex numbers, notice that we get a complex number back like this. Let's take a look at another multiplication problem. This is actually a multiplication of conjugate pairs. And so let's consider this conjugate pair, 2 minus 3i and 2 plus 3i. This will be important for us when we go to division. So I want to highlight something interesting that happens with a product of these two. Notice that the only difference in these two complex numbers is one has a plus, one has a minus. And so we call these conjugate pairs because the real number is the same and the complex number or the imaginary number there is just the negative of the other. So let's consider multiplying this out longhand, and then we'll find the shortcut to this expression. So we'll start with 2 times 2, and then 2 times 3i. So that will be 4 plus 6i. Next, we'll take a look at negative 3i times 2, negative 3i times 3i. So we have negative 6i and then minus 9i squared. We'll notice that those two middle terms will cancel, positive and negative 6i. So those will cancel to 0. We'll be left with 4. And notice that the negative I squared comes up again, which is negative 1. So this negative I is, or negative 1 is equal to that I squared. So we get a plus 9 on that last number. Negative 9 times negative 1 will be plus 9. And so notice right now what we have is really we have the first number, 2, quantity squared, that's the 4, and we have the last coefficient, 3, that quantity squared, added to that. So this conjugate pair becomes kind of what we would call a difference of squares, but in this case, it would be a sum of squares because we are dealing with some complex units on the back end. So this would simplify just down to 13, or just a real number. So there's no imaginary units in this solution. So whenever you have conjugate pairs for these complex numbers, you'll always get a real number back when you do the multiplication. This is really helpful when we need to go and use division with complex numbers. And that's what we're going to take a look at next. So conjugate pairs here will give us a real number back when we do a multiplication. So let's take a look at some division. I want to divide the complex numbers 2 plus I and 3 minus 2I. Now, this is really one very similar denominator to what we started with, but not quite. So let's take a look at how we would approach this. This is going to be very similar to how we thought about rationalizing a radical denominator. So let's start with the move of actually multiplying by the conjugate of the denominator. So when I want to simplify, I'm going to multiply by the conjugate of that denominator, which would be 3 plus 2i, and I'll multiply 3 plus 2i on the top as well. So again, multiplying by the conjugate, a form of 1. So I'm not changing the value of the expression, but I am going to hopefully get rid of the complex numbers that are in the denominator. So let's take this product now. In the numerator, we'll have 2 and 3, and then we'll have the 2 times 2i. So this will be 6, and then plus 4i. We'll do a few more arrows here, I and 3, and I and 2i. So we get 3i, and then plus 2i squared. This is all over the conjugate product here. And so what we learned in the last problem was if I have a conjugate product, we can take a shortcut here and square the first value. So 3 squared is 9. And we'll square the last value, which is the 2. So that would be 4, and we'll add those two things together. So let's continue to simplify here on this expression. So we have 3i and 4i in the numerator. So we have 6 plus 7i. This value here, 2i squared, just becomes negative 2. And then we'll divide by 13. A couple more steps we could take here. This will be equal to 4 plus 7i all over 13. And if we wanted to write it in its standard form, it would be helpful to write it as 4 divided by 13. That's our real number portion, plus 7 over 13i. So that would be our complex number in standard form with that division. So the big start to this problem is multiplying by our conjugate. and then we want to simplify it down to a complex number in the numerator. We'll take a look at one more example for this as we finish out. What if we had a complex number that is just negative I here? Well, we have kind of a choice here. If we consider what the conjugate of negative I would be, we could say that I is that conjugate. So one way we could work with this problem is just multiply by I divided by I. So we'll distribute that I to the numerator, and then we'll multiply negative I and I in the denominator. So this becomes 7I minus 4I squared in the numerator. And then we'll have divided by negative I squared in the denominator. All right, so we'll simplify this down just a little bit more. We have 7I stays the same. There's nothing to do with that. We'll remember that this I squared is negative 1, so this becomes negative 4. Negative 1 is a positive 4. And then the denominator, I squared again, is negative 1. So negative 1 times a negative is going to just be 1. So we'll just be dividing by 1 there. And if we want to kind of flip this around, this is equivalent to 4 as our real portion plus 7I as our imaginary portion. So that is the complex number in standard form in A plus BI. And that would be how we work with just a negative I or just a single I in the denominator. Okay, so that wraps up this lesson in chapter 8.1. In our next lesson, we will take a look at section 8.2, and we'll look at the trigonometric form of a complex number. So look forward to seeing you in that video. Thanks for watching.